special series of physics discussion revision is basically the support to the students preparing for the board examination. We are going to discuss the important section of our discussion of our syllabus, that is electrostatics, and in electrostatics we are going to discuss capacitors. Capacitors are electrical devices. Basically is an electrical device to store electrical energy in the form of electric field. A combination of two conductors behave as a capacitor. It means if two conductors are kept near to each other, we can store electrical energy. How this is possible, that we will understand in this way. Let us consider there are two conductors of any shape, and one is given positive charge and the other is given negative charge. So due to the properties of electrostatics, the positive charge will come to this side and negative charge will come to this side. As a result, electric field lines will be created, and there is an electric field that is created, and some electric field lines are going in this way. Positive and negative charge have gathered in front of each other according to the rule of electrostatics. So in capacitor, the space between the two conductors, this is conductor 1 and this is conductor 2. So the space between the conductors is filled with the electric field, so energy is stored in it, and this arrangement behaves as a capacitor. The volume between the two conductors stores the electric field. It means energy is stored between the two surfaces, and the capacitor and the conductor is a capacitor like behavior. Whether we give charge or not, that is a secondary matter, but the conductor arrangement will behave as a capacitor. Just for example, when we give water in the bucket, then also it is bucket, and if no water is in the bucket, then also it is bucket. So in the same way, we can take the capacitor analogous with the bucket, and charge can be treated as the water filled in it and energy is stored in it. Now here one term is there, charge on the plates of capacitor. This is a very common term, charge on the plate of capacitor. Actually the net charge on the capacitor is 0, but charge on the plate of capacitor means charge on positive plate of capacitor, positive plate of capacitor. In this arrangement of conductors, what we have observed that some lines of force are wasted. This lines of force is wasted. So in order to make a better capacitor, what we need to make an arrangement where the wastage of lines of force is minimum. For example, I am giving you the two structure. One structure is in this way and one structure is in this way. Both are given charge. This is arrangement A, this is arrangement B, which can be considered to be effective for the capacitor, which is a better arrangement for capacitor. Naturally, A is the better arrangement for capacitor. Why? The wastage of electric lines of force is minimum, whereas here you can see the wastage of electric lines of force is more. So this arrangement is better for your capacitor. Now what I would like to discuss with you people, that the best arrangement, if we can think, is of parallel plate capacitor. Parallel plate capacitor, best arrangement is the parallel plates. Why? Because if in case of parallel plates we are considering the parallel plates, then what will you observe? You will observe that the wastage of lines of force will be minimum. Also, equal and opposite charge develops on this side and this side. It is not essential that always equal and opposite charge has to be given to the plates of capacitor. Even though we are giving unequal charge, then also the charge will be same only. and here the electric field is generated, and when electric field is generated, we are getting the energy, electrical energy is stored between the plates. Here the electric field is 0, and here also the electric field is 0. Why? Because due to this positive charge, the electric field here will have this direction, and due to this charge, the electric field will have this direction, so it is 0. Similarly, here the electric field due to this positive charge will have this direction, and due to this negative charge will have this direction, and this is 0. So electric field is confined in the region, and we are able to store the energy in between the two plates. So now onwards we will discuss the parallel plate capacitor. That means the capacitor in which the plates are parallel, so that the wastage of electric lines of force can be minimized. Now, for example, what I would like to tell you, here you see that the two conductors are given, parallel plates are given. Suppose it is given 3q charge and it is given minus 2q charge. In this situation, what the distribution of charge we can understand that 3q minus 2q, that is q charge will be distributed on this outer surface and this outer surface. That means q by 2 will be here and q by 2 will be here. So what we have to take in this ground, here on this surface the charge will be 3q minus q by 2, that is 5q by 2. And what will be the charge on this surface? Here also minus 2q minus q by 2, that is minus 5q by 2. So what we observe, whatever will be the charge, whether equal or unequal charge is given to the capacitor plate, charge on the inner surface facing each other will be equal and opposite in nature. It is not important that what magnitude of charge we are giving. So this is the arrangement of charge in a parallel plate. In this situation, here you see when the electric field is generated, as a result potential difference develops between the plates. So potential difference magnitude delta V is equals to E into D, where D is the separation between the plates. This is separation. This is separation between the plates. This potential difference has an upper limit for a given two surfaces, for a given combination of two surfaces. We are not supposed to exceed the value of this potential difference more than that upper limit. Otherwise, the property of surface will change. We know that whenever charge is given to a conductor, its potential raises or potential difference increases. So we can say Q is proportional to V. This V is potential difference between the plates of the conductor. So Q is proportional to V. Therefore, Q is equals to CV. Here C is a constant and it depends upon the size, shape and placing of conductor. C is called capacitance. Now try to understand. C is equals to Q by V, that is Coulomb per volt, called Farad. Now here, why it is called capacitance? Because in this arrangement what we observe, that if we are giving a small value of Q and there is a very large potential difference generated, then naturally the value of C will be very small, so it is not a good arrangement and it is of no use. On the other hand, if a very large value of Q is given and there is a very small value of potential difference, then C will be very large and large amount of charge can be stored, which generates electric field and hence electrical energy is stored and better capacity will be there. So C is basically representing the capacitance of a conductor. One thing also important to understand, C does not depend upon Q. C does not depend upon V. If you increase Q, V will also increase in the same proportion. So this remains constant. So C depends upon the shape, size and placing of conductor. We are talking about parallel plate, so parallel plate. Now we would like to understand, now our discussion will be on parallel plate conductors only. One more thing you are supposed to understand, that if we are considering the two plates, parallel plates, in this way, one is given charge plus Q and other is given minus Q, and the electric field is generated and D is the separation between the plates, then the potential difference between the plates, delta V, is basically the difference of potential of positive plate minus potential of negative plate. So this is the meaning of your potential difference between the plates. This is positive plate, electric potential of positive plate. Similarly, this is electric potential of negative plate. How can we find the capacitance of the conductor, arrangement of conductor? That means capacitance find करने को method क्या हो. So in order to find the capacitance, so basically we want to discuss calculation of capacitance. In the process of calculation of capacitance, we have to understand that there are few steps that we have to follow. What are those steps? Steps that we have to take. First step, give plus Q and minus Q charge to the plates. Second step is there, find electric field between the plates. Now you have to understand this electric field can be constant also and variable also. Third step is to find electric field. Now electric field, third step is to find not electric field, potential difference. Now potential difference, delta V will have two values. One, if variable is there, we can find delta V is equals to integration E dr, and if constant is there, we can find delta V is equals to E dot t. And fourth step is C is equals to Q by delta V. In this way, the capacitance, where C is what? C is the capacitance of combination of conductor, and that is basically your parallel plate. Let us try to understand this thing by an example. Suppose parallel plate capacitor is there. Suppose parallel plate capacitor is there with plate area equal to A and separation between the plates is equals to D, and you have given the question, find capacitance. In this situation, if we are trying to find, here the two plates are there, parallel plates are there, on which first step to give charge to the parallel plates. Second step to find electric field. Now what you have to understand, here is the electric field confined in the region. Now we have read in the Gauss theorem, E is equals to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. Why I have written this? Due to positive charge, the value of electric field is in this direction, and due to negative charge, the value of electric field is in this direction. So these two fields are, this is due to positive charge and this is due to negative charge. Both have got the same direction. So what we are getting, What is sigma? Sigma is basically surface charge density, that is Q by A. So E is equals to how much? E is equals to sigma by epsilon naught. Also electric field is constant. So what is the next step to find the potential difference? E is equals to delta V by D. So delta V is equals to E into D, that is E is your sigma by epsilon naught into D. Therefore delta V is equals to sigma is what? Q by A epsilon naught into D. Therefore C is equals to Q by delta V, that is epsilon naught A by D. So C is equals to epsilon naught A by D. This is the capacitance of the parallel plate capacitor. This is the capacitance of the parallel plate capacitor. It is very important to understand that capacitance depends upon area. If area is increased, capacitance will increase. Capacitance depends upon the distance between the plates. This is the distance between the plates, and if distance is increased, capacitance will decrease. And it also depends upon the medium between the two plates. Right now we have supposed that it is the air, but we can replace it by some other medium. Now we have understood the method how to calculate the capacitance, and again we will try to apply the same concept in order to find the capacitance of a spherical capacitor. So for capacitor we need two conductors. Suppose to give a charge to one conductor and another conductor. So what is a spherical capacitor? So now our discussion is on a spherical capacitor. A spherical capacitor. Now our discussion is on a spherical capacitor. For any combination to become capacitor, two conductors are required, as I told. Here I am taking one spherical conductor and another spherical conductor. Spherical. Let us consider there are two concentric spherical conductors of radius A and B, and we have to find the capacitance of this arrangement. Now first step, what we have to do? We have to give a charge to the two conductors. We have to give a charge to the two conductors equally distributed on the inner surface, and negative charge is equally distributed on the outer surface. Here we are given with two conductors, on which two spherical conductors in which the radius is A and B as shown in the figure. Inner is given charge and outer is earthed. So this is the first step that we have done. Second step is that we have to find the electric field. Now what we are observing here, the electric field will be in this direction. You see, the electric field will be in this direction. This is the electric field. The relative separation between the electric field from here to here, you see the distance here to here, you see increasing. So this electric field is variable. Here the electric field is variable. When the electric field is variable, why? Here you see the separation is small. Here you see the separation between two lines and force is more. So electric field is variable. So we will have to first calculate the electric field, and in that process of calculating the electric field, we would like to first create a Gaussian surface. Gaussian surface of radius r. We are creating a Gaussian surface of radius r. So if we create a Gaussian surface of radius r, then by Gauss law, what we already know, by Gauss law, E into A is equals to Q in by epsilon naught. This is the thing that we are already knowing. Now E into 4 pi r square, this radius is r, Gaussian surface. Q in is your Q by epsilon naught. Therefore, E is equals to Q by 4 pi epsilon naught R square. This is variable. Why it is variable? It is variable because R is variable. R varies from A to B. So we are getting the variable electric field. So next step is what? We have got the variable electric field. What is the next step? We have to find the potential difference. So next step is to find the potential difference. Here what we shall use? The magnitude of potential difference, and we shall be using the formula E dr minus with magnitude only. We are considered with magnitude only. Why we are considered with magnitude? If positive charge is given to it, the direction of electric field is there from inward to outward. If you are giving positive charge to the outer sphere, the direction of electric field is from outward to inward. The capacitance will remain same. Only thing is that so we are taking only the magnitude. So delta V, therefore we can say delta V is equals to integration 1 by 4 pi epsilon naught. E को value कति छ? Q 4 pi epsilon naught Q by R square dr. यो dr को value कहाँ देखि कहाँ सम हुन्छ? From A to B. From A to B. So what value we are getting? We are getting the value Q by 4 pi epsilon naught 1 by A minus 1 by B, and this will give you value equals to Q by 4 pi epsilon naught B minus A by AB. This is the value of potential difference delta V. What is the next step? The fourth step that we have to follow, that capacitance C is equals to Q by delta V, that is equals to Q by 4 pi epsilon naught B minus A by A into B, and so we are getting C is equals to 4 pi epsilon naught AB by B minus A, which is our answer. This is the expression for the electric field due to, this is the expression for the electric field due to what? Due to spherical capacitor. This is the value that we are getting. Now some special cases are there. What are those special cases? That special cases we have to understand. Case 1 is there for a single sphere. For a single sphere, in this case there we are considering that there is a only one sphere, so we can assume that the next sphere is at infinity. We can assume that the outer sphere is at infinity. Therefore A is equals to R and B is equals to infinity. Hence capacitance will be what? Capacitance C is equals to 4 pi epsilon naught B into A by B. I am taking as common 1 minus A by B. This B will cancel because B is greater than A. So C is equals to 4 pi epsilon naught A, but A is R, so C is equals to 4 pi epsilon naught R. This is the formula that we are getting for a single sphere. For a single sphere, the value of capacitance depends only upon its radius. Only upon its radius. Now take the example of the second case. Second case, case 2 we are taking. Case 2 we are taking when if A is approximately equal to B and A minus B is equals to D, that is very small, very small. In this situation, the two spheres are very close to each other. I am taking the two spheres. The two spheres are very close to each other. When the two spheres are very close to each other, A, B, and A is the capital A is the surface area. So when the two spheres are very close to each other, that means A is approximately equal to B. Hence we can replace A by B. So capacitance, what will be happen to capacitance? C is equals to 4 pi epsilon naught AB by B minus A. That is 4 pi epsilon naught A square by B minus A is D. But 4 pi A square is the area. So this can be written as C is equals to 4 pi A square into epsilon by D. That is your A epsilon naught A by D. 4 pi epsilon naught A by D. So see carefully. Therefore, see what we are getting, epsilon naught A by D. In this situation, the capacitance of the, this is the situation that this is the capacitance of a parallel plate capacitor. So a spherical capacitor, when the two spheres are very close to each other, behaves as a parallel plate capacitor. Hence, we can write it, hence a spherical capacitor behaves as parallel plate capacitor if separation between the plates is very small. If the separation between concentric spheres is very small.